In December of 2025, as an ancient visitor from another star system began its long journey back out of our solar system, NASA made a decision that interrupted months of carefully planned observation schedules. Scientists redirected the James Webb Space Telescope, one of the most in-demand scientific instruments ever built, to take one final detailed look at an object leaving forever. What that final look revealed has now been confirmed, published, and verified by multiple independent research teams. And the answer is almost impossible to fully comprehend. This comet may be older than our sun, older than our solar system, possibly older than most of the stars in our galaxy. This is what NASA confirmed about Comet 3IATLAS and why scientists are calling it one of the most significant discoveries in the history of studying objects from beyond our solar system. If discoveries like this fascinate you, hit subscribe now, because we break down NASA's biggest confirmed findings in space exploration every single week. Let's start with the basic facts NASA has officially confirmed about this object. 3IATLAS was first detected on July 1st, 2025 by the Atlas Survey Telescope in Chile, immediately catching astronomers' attention because of its trajectory. The number 3 in its designation reflects its confirmed status as only the third interstellar object ever detected passing through our solar system, following Oumuamua in 2017 and Borisov in 2019. Unlike anything native to our own solar system, 3IATLAS follows a hyperbolic path so extreme that it can only be explained by an origin outside our sun's gravitational influence entirely. It came from somewhere else. It passed through. And it's now leaving permanently, never to return. NASA has confirmed, using multiple independent observatories, including Hubble, Webb, the SphereX mission, and several ground-based telescopes, that 3IATLAS displayed clear cometary activity as it approached the sun, developing a glowing coma in the beginnings of a tail as solar heating caused its ancient surface ice to release gas. Based on observations from August of 2025, NASA has confirmed the comet's nucleus measures somewhere between roughly 440 meters and 3.5 miles across, depending on which specific measurement method researchers apply, making it larger and more substantial than either of the two interstellar objects discovered before it. Here's where the story moves from simply confirming this object's existence to revealing something genuinely extraordinary about where it came from. Like this video right now, if the idea of studying material older than our own sun fascinates you, because that's exactly what NASA now believes it has found. As 3IATLAS made its closest approach to the sun in late October of 2025 and began its journey back out into deep space, its surface ice, warmed for the first time in what may have been billions of years, converted rapidly into a bright, active coma, creating an ideal opportunity for detailed observation. NASA. Scientists specifically chose this moment in December of 2025 to interrupt Webb's existing observation schedule and redirect the telescope toward the departing comet, understanding that this specific window represented a limited, unrepeatable opportunity to gather crucial data before the object faded from view permanently. Using Webb's near-infrared spectrograph instrument, astrochemist Martin Cordner, OF, NASA's Goddard Space Flight Center, led a research team that captured detailed measurements of the comet's chemical composition. What they found, now confirmed and published in the prestigious journal Nature on June 22, 2026, revealed levels of deuterium, sometimes called heavy hydrogen, roughly 30 times higher than what's typically found in comets native to our own solar system. Don't forget to subscribe before we get into exactly why that specific number matters so much, because it's the key piece of evidence behind everything NASA has now confirmed about this object's true age. Deuterium enrichment happens under very specific physical conditions, primarily linked to extremely cold temperatures present when and where ice originally forms. The dramatically elevated deuterium levels found in 3IATLAS strongly suggest this comet formed in an unusually frigid environment, colder than conditions typically found even in the most distant icy regions of our own solar system. Cordner explained that this represented a unique opportunity to study an ancient object from the distant galaxy, one that likely predates our own sun and solar system entirely, offering scientists a chance to directly examine material from a completely different time and place in our galaxy's history. But the deuterium measurements were only part of what Webb's data revealed. Researchers also detected specific isotope ratios involving carbon, comparing the relative abundance of carbon-13 to standard carbon-12 within the comet's material. Carbon-13 enrichment is a process scientists understand occurs gradually within stellar systems over enormous timescales, meaning the specific ratio measured in a given object can actually help researchers estimate roughly how old that material is. Based on these measurements, NASA's research team calculated that 3IATLAS could have origins stretching back as far as an astonishing 12 billion years. Let's sit with that number for a moment because it's almost too large to intuitively grasp. 12 billion years would place this comet's formation within a period astronomers specifically call cosmic noon, an era representing the universe's peak period of star formation, when galaxies across the cosmos were producing new stars at their highest rate in the entire history of the universe. Our own sun, by comparison, is only about 4.5 billion years old, meaning 3IATLAS, if this upper age estimate holds true, could be nearly 3 times older than our entire solar system. To put that timescale into a more tangible perspective, if you compressed the entire history of the universe into a single 24-hour day, our sun and solar system wouldn't have formed until roughly around 9 o'clock at night, with humanity's entire recorded history occupying only the final fraction of a second before midnight. 3IATLAS, by comparison, may have formed sometime around midday, hundreds of millions of years before our Siculcate, and even began to take shape, making it a physical relic from a genuinely different chapter of the universe's history. Here's the part that has genuinely stunned researchers working on this confirmation. Make sure you're subscribed, because understanding exactly how old this makes the comet, compared to everything else we know, is central to why NASA describes this as such a significant finding. At its upper age estimate, 3IATLAS would be nearly as old as the Milky Way galaxy itself, generally estimated at around 13.6 billion years, and would sit remarkably close to the estimated age of the universe as a whole. Earlier estimates of the comet's age, before this newest, more detailed Webb data was fully analyzed, had placed it somewhere between 3 billion and 11 billion years old. This newest research has narrowed and refined that range considerably, pointing specifically toward an origin closer to that extraordinary 12 billion year mark, based on the specific combination of isotope ratios Webb's instruments were able to detect. NASA's findings weren't confirmed in isolation either, and that independent verification matters enormously for how confidently scientists can now discuss these results. A separate research team, using the European Southern Observatory's Very Large Telescope, and led by astronomer Cyrielle Aupetom of the University of Edinburgh, conducted complementary observations analyzing the comet's carbon and nitrogen content, specifically in the form of a chemical compound called cyanide. Those findings, published alongside Webb's results, reinforced and supported the same conclusions, giving researchers strong, independently verified confidence in this remarkable age estimate, rather than relying on a single dataset from a single instrument. Stephanie Meelam, a co-author on the research from NASA Goddard, explained why finding these specific rare isotopes carries significance well beyond simply determining one object's age. She noted that the bigger picture involves examining the possibilities of prebiotic chemistry occurring elsewhere in the galaxy, pointing out that our own solar system and Earth remain the only place in the entire universe where scientists currently know chemical ingredients successfully came together to produce life. Studying interstellar objects like 3IATLAS, she explained, represents a genuine step toward understanding how common, or how rare, the specific conditions necessary for life might actually be across the broader universe. That framing reveals why this discovery extends so far beyond simple curiosity about one unusual comet's age. If 3IATLAS truly formed roughly 12 billion years ago, during the universe's peak era of star formation, then studying its chemistry offers scientists something they've never had direct access to before. A genuine physical sample of material from a galactic environment far older and fundamentally different from the one that eventually produced our own sun, our own solar system, and ultimately life on Earth. It's worth pausing to compare 3IATLAS against the 2 interstellar objects discovered before it, because this newest confirmation places 3IATLAS in a genuinely different category. Oumuamua, discovered in 2017, generated years of scientific debate, partly because it showed no clear cometary activity at all, no visible coma, no detectable gas release, leaving researchers with far less chemical data to work with when trying to estimate its age or origin. Borisov, discovered in 2019, behaved more like a familiar comet, releasing gas and dust as it approached the sun, but researchers were never able to gather isotope data anywhere near as detailed or conclusive as what Webb captured from 3IATLAS. This newest interstellar visitor, thanks to a combination of favorable timing, a genuinely active coma, and the coordinated deployment of Webb's exceptionally sensitive spectroscopic instruments, has now provided scientists with by far the most detailed, most confidently dated chemical profile of any interstellar object ever studied. There's also a race against time element woven throughout this entire story that adds real weight to why NASA moved so quickly to gather this data. As of March 2026, 3IATLAS continued hurtling outward through our solar system, making its closest approach to Jupiter in mid-March, passing within roughly 33 million miles of the gas giant, considerably closer than it ever came to Earth. From there, astronomers have calculated the comet will continue its outward journey, crossing Saturn's orbit later this year, Uranus's orbit in April of 2027, and finally Neptune's orbit in March of 2028, before leaving our solar system permanently and disappearing back into interstellar space, never to be observed again. That timeline explains exactly why NASA's decision to interrupt Webb's planned observation schedule back in December, pas a vu, 2025 mattered so much. Once 3IATLAS crosses beyond Neptune's orbit and continues fading into deep space, the opportunity to gather this kind of detailed chemical data disappears permanently. Whatever wasn't captured during this narrow observational window, while the comet remained close enough and active enough to study in detail, is now lost for good, at least until another interstellar visitor happens to pass close enough for telescopes to study it with similar precision, an event that, based on the pace of these three discoveries so far, could be years away. NASA has also confirmed the impressively wide coalition of scientific instruments that contributed to studying 3IATLAS throughout its passage through our solar system, beyond just Webb and the European Southern Observatory. Hubble, TESS, the Swift Observatory, SphereX, NASA's Perseverance, Mars rover, the Mars Reconnaissance Orbiter, the MAVEN mission, Europa Clipper, the Lucy and Psyche spacecraft, the Parker Solar Probe, Punch, and the joint ESA and NASA SOHO mission all contributed observations at various points during the comet's journey. That remarkably broad, coordinated scientific effort reflects just how significant researchers considered this specific opportunity, mobilizing an enormous portion of humanity's active space observation infrastructure to study a single object passing through on a one-way trip that will never repeat. Researchers involved in this confirmed research have been careful to note that while the isotope evidence strongly supports an extremely ancient origin, refining the exact age within that broad range, somewhere between roughly 10 and 12 billion years, according to the most recent analysis, remains an active area of ongoing study. Scientists continue working through the full dataset gathered during 3IATLAS's passage, hoping to build an increasingly precise picture of exactly when and under what specific galactic conditions this remarkable object first formed. Let's take a closer look at exactly how scientists calculate an object's age using nothing but isotope ratios measured from millions of miles away, because the science behind this confirmation is genuinely remarkable in its own right. Every chemical element can exist in slightly different forms, called isotopes, atoms of the same element containing different numbers of neutrons in their nucleus. Deuterium, for instance, is simply hydrogen with an extra neutron, making it slightly heavier than the standard, much more common form of hydrogen found throughout the universe. Similarly, carbon-13 is a slightly heavier version of standard carbon-12, distinguished by one additional neutron. The relative abundance of these heavier isotopes compared to their more common counterparts isn't random. It's directly influenced by the specific physical conditions present when and where a given batch of ice or gas originally formed, including temperature, radiation exposure, and how actively evolving stellar environment. Colder formation environments tend to produce higher deuterium enrichment, since certain chemical reactions that concentrate deuterium into ice become increasingly favored as temperatures drop toward absolute zero. Similarly, gradual enrichment of carbon-13 relative to carbon-12 tends to accumulate over enormous timescales, as galaxies undergo successive generations of star formation, each generation slightly altering the overall chemical makeup of the surrounding interstellar material through the process of stellar nucleosynthesis, the nuclear reactions occurring inside stars that produce heavier elements over a star's lifetime. By carefully measuring both of these isotope ratios within 3IATLAS's coma and comparing them against well-established models of how these ratios evolve over cosmic time, NASA's research team was able to work backward, essentially reconstructing rough estimates of both the temperature of the environment where this comet's ice originally formed, and roughly how long ago that formation likely occurred relative to the broader chemical evolution of our galaxy. It's a remarkably indirect method, using nothing but chemical fingerprints measured from millions of miles away, and yet it represents one of the only tools scientists currently have for estimating the age of material that predates any direct historical record, any written observation, or any other conventional method available to astronomers. It's also worth understanding just how unusual it is for researchers to interrupt Webb's carefully planned observation schedule in the way NASA did in December of 2025. The James Webb Space Telescope operates on an extraordinarily competitive, oversubscribed observation schedule, with astronomers around the world submitting detailed proposals months or even years in advance, competing for a strictly limited amount of available telescope time. Interrupting that schedule to accommodate an unplanned TIMOI, a sensitive opportunity, requires special approval, reflecting just how significant NASA and the broader astronomical community considered this specific window for studying 3IATLAS before it faded from observable range entirely. That urgency paid off because researchers acted quickly, capturing detailed spectroscopic data during the exact window when 3IATLAS's coma was brightest and most chemically active following its closest approach to the Sun. They were able to gather data precise enough to produce these remarkably specific and now independently confirmed age estimates. Had that observation opportunity been delayed even by a matter of weeks. As the comet continued cooling and its coma activity diminished on its outward journey, the resulting data may not have been detailed enough to support such confident conclusions about the object's extraordinary age. Looking ahead, researchers continue analyzing the full dataset gathered from 3I-ATLAS throughout its passage through OUR's solar system, working to extract every possible detail before the comet becomes too distant and faint to study effectively. With confirmed contributions from over a dozen different NASA and international space assets, this represents one of the most thoroughly documented interstellar object passages in the short history of this entire field of study, a comprehensive scientific record that researchers expect to continue analyzing and publishing findings from for years to come, long after 3I-ATLAS itself has disappeared permanently back into the depths of interstellar space. For now, what NASA has officially confirmed represents one of the most significant findings ever gathered from an interstellar visitor. A comet, quite possibly older than our entire solar system, potentially formed during the universe's most active period of star formation, carrying chemical signatures unlike anything found among comets native to our own solar neighborhood, now confirmed through multiple independent research teams using some of the most powerful telescopes ever built. As 3I-ATLAS continues its irreversible journey outward, past Jupiter, past Saturn, eventually past Neptune, and finally back into the interstellar darkness it emerged from, it carries with it confirmed evidence of a time and place in our galaxy's history that humanity has never before had the opportunity to study this directly. If this story gave you a new appreciation for just how ancient some objects passing through our solar system can be, make sure you're subscribed because there are more. Confirmed discoveries like this coming every week. Hit like, drop a comment, letting me know what you think the next interstellar visitor might reveal, and I'll see you in the next video.